trapped in empty space, and today Dan and Harlow will start telling us about quantum information and entanglement in incredibly densely filled space. Quantum information of black holes.
All right, thanks, Patrick. Yeah, thanks for the invitation. It's great to be back at the Hebrew University. Looking forward to the lectures. My goal here is to give you guys sort of as much of an introduction as is reasonable to fit into 4 lectures, into sort of both the sort of classic tools for thinking about black holes, and then also some of the newer information theoretic tools. You know, it's going to be tough, you know, given the broad background of people here, and I'm going to try to start from the beginning, but I'm not necessarily going to explain everything carefully. I'll try to be logically complete, but things might go by only once. So if you're getting lost, it's up to you to ask me, okay? I'll do my best, and I'll try and sort of gauge as we're going on and speed up or slow down, but feedback is appreciated. Before I begin, though, I just wanted to get a rough idea. So can you raise your hand if you're sort of, thanks, Rob. So raise your hand if you've sort of ever encountered the idea of a space-time metric before, and maybe, you know, written one down. Okay, good. You're not sure, Ning? You're okay with S-duality, but not with... Yeah. All right. Okay, so in that case, I think I can safely begin by writing down the Schwarzschild geometry. So I should say, you know, today the goal is going to just be to talk about some of the classical properties of black holes, and then to start getting into some features of entanglement in quantum field theory. So some of that Rob also talked about it. So there will be some overlap, but you know, I have a different agenda than he does. And in any event, it's not bad to hear things more than once. Okay, so the Schwarzschild metric is the unique spherically symmetric solution of Einstein's equation without any matter present. So if there's matter present, then you can have more general solutions, of course, you know, stars, this kind of thing. But without stars and with spherical symmetry, oh, and with one other important criterion, which I'm about to say, this is all you get. So the additional important criterion is that as this coordinate r becomes large, then this factor here becomes 1, and this just becomes the metric of ordinary Minkowski space. So just for the few people who didn't raise your hands, briefly, a metric is just some way of describing the geometry of spacetime. You can think of it locally as an inner product that tells you the lengths and angles of vectors as a function of position. So I've written it out here in terms of the invariant line element, but roughly you can think of this, for example. So say so this coordinate r, say I just have a little bit of displacement of coordinate r, then to find out the actual physical length of that displacement, I take the square root of this, and then, you know, the square root of this times that displacement gives you the actual physical length. Okay, and that's really the meaning of this metric. And then so like I said, as r goes to infinity, you just get this, and then this is just, you know, the dx squared plus dy squared plus dz squared in polar coordinates. Okay. Okay, now, so this is the Schwarzschild geometry. Clearly, there are 2 interesting values of r in the Schwarzschild geometry. There's r equals 0, and there's r equals 2gm. Other than that, this is just, you know, these are just some functions. But there, it looks like, well, the metric might be becoming singular. So at r equals 0, so this is called the singularity. And by the name, you can guess that the singularity there is actually real. Okay. So as you approach r equals 0 in these coordinates, the tidal forces in the space-time on some observer, you know, or some, let's just say, some object who's moving through the space-time, are actually divergent. And one way you can quantify that is by the diverging square of the Riemann tensor, if you know what that is. Now those divergences are probably regulated by Planck scale physics. I don't think that would make you feel much better about it, though, if you happen to fall into the singularity yourself.
Why do you square it? It's also the Ricci scalar.
Well, the Ricci scalar is 0, so that's the thing. This is a vacuum solution of Einstein's equation, so the Ricci tensor is 0. So you have to actually take the Riemann tensor and square it. Yeah.
Yeah, about the singularity, wouldn't it take for us as external observers infinitely long until the black hole, I mean the star, when it collapses, actually reaches the singularity?
Yeah, and we're gonna talk about that. But if you actually jump in, then you reach it in finite time. Yeah. So and that's, actually in most of these lectures, we're not actually going to say very much about the singularity, which is actually kind of embarrassing, because in some sense you would think that that's where all the mystery should come from, but somehow we'll find that we'll be able to get very confused without actually having to talk about the singularity. Okay. So okay, that's the singularity. The other interesting radius, of course, is r equals 2gm. So this radius is so important, I'll give it a name. It's the Schwarzschild radius, rs. Oh, I should say, yeah, if you're one of the people who keeps track of units, so I'm also working in Robb's units, where c equals h bar equals Boltzmann's constant equals 1. And actually, pretty soon I'm going to start setting the Schwarzschild radius to 1, too, for a while. Yeah, he said it was because he was lazy, but I mean, I think this is a principled stand, I mean, this is like deciding that we're no longer going to use the king's foot to measure length. Okay. So now at this radius, yeah, I just brought it up because there would be an over c squared here otherwise. Okay. So unlike r equals 0, I'm going to try and convince you in a few minutes that this is not actually a singularity, that this is a perfectly smooth point in the space-time, and that locally, if you happen to find yourself in the vicinity of this radius, you wouldn't think that particularly much was going on there. Okay? Now, that's a local statement. Globally, it's clear that something is going on here. Well, what is it? Well, if we look at the metric here, for r less than 2gm, the signs change. Okay? Which means that for r less than 2gm, the r coordinate is time-like. Okay? What does that mean? Well, it means that once, say you start out at r greater than 2gm and you fall in, beyond that point, you can no longer stop r. It's just as hard to stop r from decreasing as it is for us to stop time increasing, which means you can't do it. Which means that once you're past here, once you're at r less than 2gm, you're on a one-way trip to the singularity. Now, maybe let me just comment again, just for people who maybe haven't seen this before. So if you happen to be in the region where r is much greater than rs, okay, then you can work out the motions of test particles in this geometry. You can just figure out what did they do. And you find that they behave as if they were just obeying the ordinary Newtonian gravity, responding to some sort of Coulomb-type potential of a point mass with mass m. Okay, so far this m was just some parameter that appeared in this metric. But it really is the mass. In some sense, a mass. At least it's a mass in the sense of someone who's out at large r thinks that they're moving around some point mass m. Okay. Now, I've been trying to be careful to not actually call this a black hole, because this geometry is not actually by itself describing a black hole in the conventional sense of what we usually mean by a black hole. And I'll get soon to what is. So I'm going to try and just refer to it as the Schwarzschild geometry for now. And you'll see soon why I don't want to call it a black hole. Okay. Now, another important point, though, about the region r less than rs. Okay, so yeah, and this was this implies Newton. Good. Okay. Now in the region where r is less than rs, so as I said, you can't stop yourself from falling into the singularity, and actually that happens to be true even if you happen to be a massless particle. And what that means is that if you being you fall in, and you want to send a message to me, who's out in this region, you can't do it. Because you'll send photons, you'll send whatever you can try and send, but whatever you try and send also isn't going to be able to get out of this region. So when you have that kind of situation, when you have a region in the space-time which can't send signals to another region, and usually, typically the other region actually is taken to be an asymptotically flat region, let's say to start with, like the large R region here, then you say there's a horizon. And the horizon, usually actually the event horizon, cuts the space-time into the part that can send signals to infinity and the part that can't send signals to infinity. So this radius is usually called the horizon. This surface, this is a surface in space-time. Okay. Now, just one more sort of just basic comment about this geometry before I go on, is that so it has there's a gravitational redshift here coming from this term. So what does that mean? It means that if you sit at constant r, then as you move r closer to 2 GM, this thing here is getting smaller and smaller, which means that you need more and more coordinate time. You need a larger and larger dt to get the same amount of proper time, which you get from this. Okay, so what that means is that, well, it can mean one of two things. So say I'm standing outside and you're being lowered sort of on an elevator down towards the horizon. Then I'm going to see your clock going slower and slower. Okay, any signal you send, I'm going to see get more and more redshifted. And as you approach the horizon, actually, anything you do will take an infinite. The time it takes, from my point of view, out at infinity, where dt is a good coordinate, is unbounded. Okay, so that's called the gravitational redshift. And that's actually extremely important. So that's why I wanted to mention it just from the beginning. This gravitational redshift, it's sort of a stretching of space-time, which allows extremely short distance physics near the horizon to be visible to somebody out at infinity doing low energy experiments. Well, really probably I should call them low energy thought experiments.
The horizon is two-dimensional or three-dimensional?
Yeah, so really it's you can think of it either way. So I think using the way I've been describing it, it's three-dimensional. And then I think that usually people define it as, if you imagine a Cauchy surface, then it's the intersection of the Cauchy surface with that gives you the two-dimensional horizon. Yeah. Good question though. Okay. Oh, maybe just one other comment. So yeah, about this Newtonian thing. So yeah, clearly when r is bigger than 2 GM, there's sort of an interesting expansion in r over 2 GM. And the leading order corrections in r in sort of 1 over, let's call it 2 GM over r. So that's the small thing. The leading order corrections of that are responsible for almost all of the experimental tests of general relativity. Okay, so that's essentially, we can also test it doing a few other things in cosmology, but almost all of them come from looking at the 2 GM over r corrections to the Schwarzschild metric. Yeah. Yeah.
Does it mean that if we have some kind of Hamiltonian,
yeah,
the eigenvalue can be unbounded to the negative?
Yeah, so no, it doesn't mean that. But defining energy is very confusing in gravity. I will eventually talk about it, but not for a while. Let me just very briefly say that the energy is really only defined with respect to the time translation symmetry at infinity. So you just you can describe everything in terms of, if you want to get a good sense of what the energy of something is, you have to trace it back to the boundary and see where it came from. You have to see what its energy was back out where it's sensible to where it's sort of easy to define energy. I mean, there is a definition that works more generally, but if you just stare at it, it's not obvious always what the energy of something is. Yeah.
So you said that But the time becomes space-like.
Yeah, yeah. As it hit better.
That then you can also go in whatever direction.
That's correct. Yeah, yeah. So because remember, so this is the confusing thing if you're not familiar with this kind of thing, is that these are just coordinates. So it's so that the coordinate t becomes space-like inside, and yeah, you can walk in forward, back and forth in t inside the horizon.
There could be totally normal life there, except for the highest process.
Yeah, absolutely. So yeah, it's worth saying. So yeah, in this so say you're in this region where r is less than rs, but let's just say rs is ridiculously big. The size of the observable universe. Then yeah, I mean we could be there. We could build the LHC and discover the standard model.
No, you can show that you go into the singularity in finite proper time.
Yeah, that's correct. But that proper time is proportional to rs. So if rs is ridiculously large, yeah.
But don't all the light cones head towards a singularity?
Yes.
I mean, so in that sense.
So yeah, so eventually we and our LHC, we will die, but we've got some time to. I mean, we're going to die anyway, right? So. Okay. Yeah. So yeah, that's sort of just the basic intro to Schwarzschild. Okay, we can get rid of the dimensionful rant now.
Your point about the gravitational redshift permitting low energy experiments at infinity.
Oh, yeah. So say that I have a laser, or say that I've got two lasers that can somehow I can do UV, I can do very high energy collisions and look and get the products. Well, let me say the simpler version first. I have a laser that shoots very high energy photons. If you dangle me on a string near the horizon and I shoot my laser out, it can look as low energy as we like. Okay. Now build that into a scattering experiment to get an invariant. Yeah. Okay. All right. So yeah. Now I want to. So I claimed that this was not singular, but now to demonstrate that I'm going to now need to do a little bit of work. Okay. So the idea is that I want to introduce what's called the Kruskal extension. So to give you a sense of what the full geometry looks like. So far we sort of, these coordinates do something funny at a certain point, and it's not clear exactly what the global picture of the space-time is. So we're going to need to introduce new coordinates. So I'm not going to touch the sphere coordinates because this has spherical symmetry, so it's nice to keep that. But I'm going to do some reshuffling of t and r, which makes the global picture more explicit. Well, maybe not completely obviously, but a good thing to do is to try and pick coordinates which are better suited to describing what null geodesics are doing. So null geodesics are the trajectories that massless particles move on. And if I can pick coordinates that are aligned with null geodesics, then anywhere the photons can go, those coordinates are going to go too. Okay, and so by finding such a set of coordinates, we can figure out what the full space-time is. Now, in order to do that, of course, I have to first figure out what the null geodesics are. So I'm only going to be interested in radial null geodesics that don't have any angular momentum. So they're just going straight in or coming straight out. So then, okay, so of course I'm not going to solve the equation for you. I'll just tell you what the answer is. So the trajectories look something like this, where r star is r plus log. Okay, so starting here, 2gm is 1. Okay, and that's going to continue for the rest of the lecture. Just it simplifies equations, and it's crazy not to do it. So this r star happens to be called the tortoise coordinate. So one interesting property of the tortoise coordinate is at large r, it approaches r. Now, okay, you might say it doesn't because this gets infinitely big, but this gets much more infinitely big. So sort of in ratio, it approaches the ordinary Schwarzschild coordinate. But then as you approach the horizon, which is now at r equals 1, then this goes to negative infinity. Okay, so these are coordinates which just describe the outside. Okay. Now you might say that that sounds like I'm not making progress since now I'm only defining the outside, but have faith. So this is just the simplest way to describe null geodesics in the Schwarzschild coordinates. Okay. So the thing that we want to do then is define new coordinates, u and v, as e. So u is going to be minus e to the r star minus t over 2. And v is going to be e to the r star plus t over 2. Now, of course, the goal here is that, so you see there's this plus or minus here, and there's this c. So what these coordinates do is they parameterize null geodesics. So a line of fixed u is a line of fixed r star minus t. So that's one of these geodesics. And a line of fixed v is one of the a null geodesic with the other sign choice here. Okay. I hope my u's don't look too much like v's. I can try and. Okay. And the u and v happen to have the convenient property that u times v is 1 minus r times e to the r. Okay, so given a u and a v, it's not too hard to turn it back into an r. Okay, so given a formula like this, you can rewrite the metric in the new coordinates. Okay, so what do you get? Well, you get something like see, is that so you get du dv plus dv du plus r squared d omega squared. So you could ask, why did I keep the r's around since I just changed to u and v? And of course, the answer is that it's kind of annoying to solve this equation. So you should think of this r as being implicitly expressed in terms of u and v. Yes?
Wouldn't one go to the falling coordinates and then you don't have to worry about the r's because the geodesics
Well, that's essentially what I've done here, right? Because these u's and v's are null geodesics.
But then instead of dt, you'd use d tau, I mean the coordinate of the
Oh.
radio.
Yeah, so you want to use massive geodesics.
In a sense.
Yeah, so you could. So that's another coordinate system. I guess it's called rain coordinates, or maybe Panleve-Gullstrand. I forget exactly.
And then from there you can go to null, because then ds squared is 0 and you get once again. But without the
yeah, so you can, but that's just another intermediate step. And I already feel guilty about the number of coordinate systems I'm going to introduce in this lecture. So. And in fact, I'm going to introduce one more right now, because this business of the metric being off diagonal, I have du dv times dv du, is not necessarily the most intuitive thing in the world. So then the obvious thing to do to fix that, or at least obvious to me, I don't know, is you define sort of a plus and minus version of these guys to go back to something where t is time-like and x is space-like. Yeah? This? So R star is this? Okay, so these are trajectories. Okay, so just this, I'm writing t as a function of r, so that's picking out a line in the TR plane, and that line is a null geodesic. This C labels which geodesic I'm talking about, and the sign plus or minus labels whether it's going to the right or to the left. Okay? All right. So, okay, now hallelujah, we can write the Kruskal, I guess it's called Kruskal Caesaricus. I don't know, I'm not from Eastern Europe, so I don't know how to say that. Okay, so this is exactly the same geometry, but now written in terms of new coordinates. So what do we learn from this? Well, the first thing we learn is that nothing interesting is happening at r equals 1. Okay? This looks completely non-singular at r equals 1. So we've successfully removed any appearance of a singularity at the horizon. Now, before I can tell you what the full space-time looks like, though, we need to figure out what the ranges of these coordinates are. The obvious thing to do, though, is to see that nothing goes wrong if I imagine that both capital T and capital X are allowed to run from minus infinity to infinity. Okay? Just to be clear, so it may not, because of this implicitness, it might not immediately be clear that that's the case. But remember that, so UV is this. And so, by, algebra, that's this, okay? So, so now as r goes from 0 to infinity, this quantity can go from, let's see, so from, it looks like from -1, let's see, no, sorry, from 1 to minus infinity, okay? Yeah, but r star has disappeared from the discussion. So I've just related r directly to capital T and capital X, and I've written the metric in terms of just little r and then capital T and capital X. So you can forget about r star. So yeah, from the point of view of r star, I've done some sort of non-trivial analytic continuation, but I hid that by not writing things in terms of r star. So okay, the best way to explain this though is to just draw a picture, as is usually the case. So here's a picture. So this is the x t plane, okay? Which remember this is somehow the RT plane is the same as the TX plane, at least up to which regions are included. And now let me just draw where what the various coordinate regions are. So we saw that t squared minus x squared has to be greater than -1, I think, if I got the signs right. So what that means is that there's a hyperboloid here. And so this hyperboloid has two sheets, and it's the t squared minus x squared equals 1 hyperbola. Okay. This quantity has to be less than 1, but usually this is minus what we call the variant. Yeah. Okay. So the coordinates t and x going from plus infinity to the minus infinity aren't quite included because we need to impose that r is positive. So then that just gives us the region in between these two hyperboloids. Now there's two, so I should have drawn these first probably because I wanted the hyperboloids to asymptote to them. Okay, so this line here is u equals 0, and this line here is v equals 0. Okay, because u and v, so as you see from here, u and v are sort of 45-degree lines. So null geodesics move it at 45-degree lines in this picture. So r equals 0 is here, and then it's actually also here. So that was what we said here. So if r equals 0, then this is 1. So that's this hyperboloid. So okay, so maybe that's the first surprise, is that there's now two singularities. Okay. There's a r equals 0 singularity down here at the bottom of the diagram. There's an r equals 0 singularity up here at the top of the diagram. Moreover, the horizon has a more interesting structure than you might have thought. So what happens at the horizon? So that's when r equals 1. When r equals 1, this is 0. So apparently either u or v has to be 0. So this cross here is the horizon. Okay. Finally, where's asymptotic infinity? Well, at asymptotic infinity, that's when r goes to infinity. So then apparently u times v goes to minus infinity. So if u times v goes to minus infinity, then that's like saying x goes to infinity and t is fixed. But there's actually two ways to do that in this diagram, right? We can do that going this way, or we can do that going this way. So what that means is that there's actually two spatial infinities in this geometry. Out here, a good description of the geometry is that there's a point source of mass m and you're floating around and it looks like there's some kind of star someplace. But then that's actually also true out here, okay? And it's a different universe connected by a wormhole, which is this, okay? Now, the wormhole, tragically, is not traversable. Say that you start down here and you want to get to the other asymptotic region. Unfortunately, there's this 45-degree line here, which you can't go faster than. And this 45-degree line is sort of perfectly chosen so that no matter how hard you try, you're going to hit the singularity before you get through to the other region. Okay, so this is called a non-traversable wormhole. Yeah, exactly. So what you, yeah, right. So you could ask, is there any physical content to saying that there's a wormhole? So say that you live in that universe and I live in this universe. And you know, okay, we're in the land of the prophets, so we dug up some stone tablets that said at such and such time you should jump into the wormhole. Okay? So we do that. So I jump in here and you jump in there. And we'll meet in the middle. You know, and we can
Build an LHC together.
yeah, we can build an LHC together, you know, we can sing songs, and then it all ends tragically. Okay, so this now is the full picture of the Schwarzschild geometry. Okay, this is what it's like: two universes connected by a wormhole. So let me just say a little bit more about what the original coordinates look like in this picture. So you see from here that the fixed r lines are hyperboloids. So out here, constant radius lines look like this. They're hyperboloids. And you know, they eventually pile up against the horizon here. And then indeed, once I get through the horizon, now they start doing this. And you can see that it's time-like. So the slices of constant r are space-like in this region, and actually also in this region, near the past singularity. So that's consistent with what I said about the sign changing before. Similarly, the lines of constant t, well, the diagram is getting busy. Maybe time can be blue. So you know, this is t equals 0 outside. You know, and here's some time going forwards, and then actually t equals infinity is piling up right against the horizon here, and then t equals minus infinity is piling up against the horizon here. So the original Schwarzschild coordinates with r greater than 1 are just covering, you know, this wedge of the diagram, and we've discovered 3 new regions. One of them was the sort of r less than 1 region we sort of fumbled our way through before. But there's another r equals 1 region down here with another singularity, and then there's another universe out here that we had no idea about. Okay. Now, as you may have already sort of started feeling, you know, there were already sort of too many equations to come to the kind of conclusions that we wanted to. Yeah, sorry. So in here. Well, yeah. So you might say that you can see this singularity. You mean because signals can come from it. That's what you mean. Yeah. So that's true. I mean, you can jump up here and die in the other singularity. But the thing is, so whether or not you see this singularity as sort of right. So it's possible for you to see this singularity if this singularity happens to send some sort of message to you. Okay. And so that's a question about sort of the state of this geometry. You know, are there particles coming out of here, that kind of thing. Yeah, you can't go back. Yeah. I mean, once you're here, you can't go back here because you know, I mean, time. Right. So in this diagram, light is going on 45-degree lines. So say you're here, you're constrained to go forward within those 45-degree lines. Yeah. That's correct. Yeah. So I'm not calling it that because I'm not calling this a black hole at this point. Yeah. I mean, clearly this doesn't look like anything that, you know, your astrophysics friends would recognize as a black hole. So I want to reserve the term for things that they might recognize. Okay. So now, so like I said, you know. I mean, so the equations here weren't too bad, but still it was sort of too many equations to just describe the sort of coarse-grained features of the space-time that we want. You know, having to do with who can talk to who, and you know, where can signals come from. So I tried to compute the optimal Blackboard algorithm, but I'll see if it. Let's see. Oh, you know, I think actually optimality would be to write on this one first. Okay, good. All right, so now I'm going to introduce a new tool to sort of streamline the kind of analysis that we just did so that we don't have to do it again. So this is called Penrose diagrams. Okay. So so in most of these thought experiments we'd like to talk about, we don't actually care about the details of the geometry. And we've already seen some of that. I cared that these two guys can't communicate, but I didn't care about questions like exactly how much time does it take for you to get from here to here. Those are the kind of questions where it's some time, but we don't really care. So it's convenient to be able to throw away that kind of information and have a more concise way of describing the space-time. So that's what these Penrose diagrams accomplish. So the basic idea is that there's some theorem, which is not very hard to prove, which says that if you have two metrics, so here g mu nu, by that I just mean the coefficients here. So this thing you would write it as g mu nu dx mu dx nu, and then the indices are contracted here. So in this case, the g mu nu is diagonal, and you can read off its coefficients here. But more generally, it may not be diagonal, like for example in this case. So if you have two metrics which are related by the multiplication of a positive function, then you can prove, and I think I didn't put it on the homework just because I thought it was a little tedious, but you're certainly welcome to view it as a homework problem. You can prove that these two metrics share the same massless null geodesics. So a null geodesic in this metric is also a null geodesic in that metric, which means that this information of multiplying by a scalar is irrelevant for determining the causal structure of the space-time, who can communicate with who. So that's some theorem. And two metrics that are related like this are called conformally equivalent. So Penrose, being the smart guy that he is, realized that you can use this observation to sort of very elegantly describe the structure of these spacetimes in diagrams, in really compact, literally, diagrams that let you just immediately see the causal structure of the spacetime. So rather than try and give some sort of general definition, which only a mathematician would enjoy, I'm going to do it with an example. I'm going to do an example so that we can just see very concretely what I mean by this. Okay. Unfortunately, it means that I'll have to introduce one more coordinate transformation, and I think this will be the second to last one today, but there will be a break now before you get another one.
You should enjoy this as well. So.
This is good. Okay. Yeah. Well, I know. What I heard is that mathematicians actually, in their private time, they're just as intuitive as physicists. It's just when they write their papers, they remove all the intuition because they want it to look intimidating. Okay, so let's consider again just ordinary flat space. So this is just your favorite, Minkowski space that we know and love. And I'm going to work out the Penrose diagram for it. Now the goal of the Penrose diagram is to pick this factor judiciously. Okay, what do I mean by judiciously? Well, one of the annoying things about this geometry is that it's infinite. R can go to infinity, t can go to plus or minus infinity, and it's hard to fit all that on the blackboard. So then it's hard sometimes to talk about the whole space-time. But if I'm allowed to just do this, as I please, then I can pick this function to be divergent or go to 0. Actually, in this case, probably you want it to go to 0. S, R goes to infinity, or t goes to infinity, in just such a way that the boundary is now at finite geodesic distance. Okay? If I can accomplish that, then I can draw a finite picture of the space-time that has the same null geodesics as the infinite one that I started with. Okay? So the rough idea is that you want to use some function like arctangent to pull in the boundary to finite distance. So why did I pick arctangent? Well, it's just one of those functions which, if you look at the graph, it's something like that. So the domain is infinite, but the range is finite. So then you can use this to to pull an infinite interval into a finite interval. And actually, the way you do it is you define. Well, the first thing you might want to try and do is to do that directly to t and directly to r. But that turns out to be a little bit inconvenient the thing you really want to do is you want to apply it to the null combinations, like what I was doing here. So you define t plus r equals arctan of little t plus r, plus little r. So now the new coordinates are big T and big R, okay? And then, of course, the other one you define, well, okay, I'll just do this. Okay, so these are the new coordinates. I've taken the null directions in space-time and just pulled them in an infinite amount, okay? So, okay, you can work out what the metric is, and I think this I did put on the homework just to give you one example of turning these kind of things out. The metric, so it's of this form that I just described. So we've got some function out in front. Okay, so by looking at this, you can see that indeed this function is positive. And it has the property that since cosine vanishes in various places, it diverges. And it diverges in the way that we like. And then you just get something simple. So you get minus dt squared plus dr squared, and then plus some function of r, which happens to be sine of 2r over 2 in these coordinates, but it doesn't matter very much. Okay, you get that. So now, of course, the thing we want to do is we want to ignore this prefactor in front by using the theorem. So, okay, now I think I'll try this. Okay. Now, of course, I need to say what the ranges of these coordinates are. And this is one of those things where you can figure it out in the privacy of your office in a few minutes, but it's a little bit confusing to try and give a convincing explanation for it on the board. You can convince yourself that the coordinate ranges are that t plus or minus r has to be less than pi over 2, and r has to be greater than or equal to 0. So that sort of just follows from staring at this formula and remembering that little r goes from 0 to infinity and big T goes from minus infinity to infinity. So now if we draw this region in the t and r plane, what does it look like? Well, it looks like this. It's a wedge. Okay? And then the region that's this, and then the interior of this wedge is the thing that comes from that lies in these ranges. So we've succeeded. We've conformally compactified, that's what it's called, Minkowski space. So, well, I didn't quite compactify it yet because the original coordinates had this less than here. Okay? Now I compactified it. So by doing that, I included this boundary here that I hadn't previously included. Okay, this one had already been included. This one is the origin of polar coordinates. So this is r equals 0, and if you trace that through here, you'll convince yourself that that turns into little r equals 0. Okay. So and moreover, so the key point is that I preserve this structure of the metric here, which means that null geodesics in the TR plane are still 45-degree lines. And that's the goal of the Penrose diagram, is I've reduced the space-time to a finite size, but the geodesics in the original space-time are still represented by 45-degree lines. Okay? So the new boundary that we added here, this line here, has 5 interesting parts. So for reasons which you have to ask somebody from Cambridge to explain to you, the names are I plus, I minus. So that's this point here and this point here. This line here is called, I'll call it J minus. I think they call it scry. Yeah, but I couldn't even find scry in LaTeX, so I just, I'm only going to indulge these guys so much. This is J plus, and this is I0 here. Okay? I guess, well, I should probably be more consistent about the indices being up and down. I forget whether they should be up or down, but yeah, like I said, find somebody from Cambridge to explain it to you. Okay, so okay, the names just look cryptic, but what do they really mean? Well, I minus is where time-like geodesics come from in the infinite past. Okay, time-like geodesics are guys, whose slope is less than 45, less than pi over 4. So they start here, and they end here. So there's a particular one. Well, that one's probably not a geodesic. J minus is where null geodesics come from, and J plus is where null geodesics go. And I0 is where spatial geodesics end. So the names which maybe make more sense but take longer to say is that this is past time-like infinity, this is future time-like infinity, this is past null infinity, this is future null infinity, and this is spatial infinity. Okay. So to actually get to the Penrose diagram, so I drew the TR plane here, but you know, just when you're just having discussions, it's much easier to just erase these axes altogether and just look at the diagram. Just look at the wedge. Okay, so that's a Penrose diagram. So right away we see that it captures some important features of Minkowski space. One is that there aren't any horizons. So if I take, if I look at this time-like curve here, every point in the diagram is eventually going to be able to send a 45-degree line to this guy. Okay? That's different than what we found in the black hole. Okay, and we're going to see when I draw the Penrose diagram for the black hole that it's going to be different because of that. Okay, so no horizons. The other thing that you might see from this picture is that there's probably a nice description of the physics here in terms of an S matrix. In the sense that you have some state here where you can send in massless particles at J minus, you can send in massive particles at I minus, and then there's some S matrix which maps that state to the state of massless particles coming out at J plus and massive particles coming out at I plus. So just from drawing the diagram, we've learned what are probably the two most important things to know about Minkowski space, which is that it has an S matrix and that it doesn't have horizons. Okay? So now I'm going to draw the Penrose diagram for the black hole. Let's see. So now this is the confusing part of the. So I think. Yeah, probably. Okay. I think I'm going to have to trust that you remember this, and it's easy to draw again. I'm going to actually keep this formula for a sec. I probably shouldn't have erased the metric. Okay. So now for the black hole, for the Schwarzschild geometry, I should say. It shouldn't be that hard to see that once we go to the Kruskal coordinates, the same kind of arctangent kind of transformation is going to do the job for us, because we still had this, right? The metric was something involving t and x. Here these guys had infinite ranges, although they were constrained to lie within this hyperboloid, but they were still infinite out here. But I can do the same coordinate transformation that I did before, and the only difference is going to be in the coordinate ranges, because now we're going to have, there's going to be two differences. One is that, so x here was allowed to go from plus infinity to minus infinity, whereas in Minkowski space, the thing that appeared here was a radial coordinate that only went from 0 to infinity. So that cut out half the diagram. That was why we only got this wedge instead of this diamond. Okay. And then the other difference is that, so like I said, that there.
Actually, you're covering up. In the Schwarzschild case, you weren't allowed to go through R equals 0 because it was a physical singularity.
Yeah. Yeah.
In Minkowski space, R equals 0 is just a coordinate singularity.
Uh-huh.
So in principle, you could have gone through, but in that part of the discussion, which you could only do in the privacy of your office, you have to convince yourself it's a redundant description.
That's correct. That's correct. Yeah. So that's why I put it on the homework. Yeah. So okay, but at R equals, so R equals 0. So little r equals 0 here really is a real singularity, and you can't go through it. So fairly clearly, we can guess what the answer is just by looking at the answer from Minkowski space. So first we double to the diamond, like I just said, because now x can go to minus infinity. And then we just trim off the top. because we can't go above this t squared minus x squared equals 1 hyperboloid. Okay, so that was easy. So let me just draw that a little bit more carefully. I never do well in really getting these to be 45-degree lines, but okay. So this is now the Penrose diagram of the Schwarzschild geometry. So this shouldn't look that different from this picture, but the difference is now that everything is sort of very manifest. So the horizons are here. This point here, sometimes people do that, just to scare you, to tell you that you really don't want to go there, which you probably don't. And then these are the two asymptotically Minkowski regions. And now, indeed, we sort of rigorously made it clear that these are asymptotically Minkowski regions, right? There's an I0 here. There's an I0 here. There's two I minuses, two I pluses, and then you get the idea, right? So there's two J pluses, two J minuses. Okay, and then you can see very clearly that somebody on this side in this region cannot communicate with somebody who stays in this region. That's the horizon. You can see that at least for this geometry, it's probably not such a great idea to talk about it in terms of an S matrix, at least on one side, because there could be stuff going on over here, and you somehow have to be able to describe both. You could imagine probably thinking about it in terms of sending stuff from both sides and having stuff come out. So from now on, I'm essentially always going to do physics by Penrose diagram. Oh, yeah. Yeah, so remember we had this equation here, which I was careful not to erase. So in the Schwarzschild geometry, this little r is positive, because at r equals 0, there's a real physical singularity. So that puts a constraint on the t and x plane here, on the big T and big X plane. And the constraint was that this hyperboloid here is a boundary of the geometry, and there's nothing on top. Okay. So if you push that through the arctangent transformation I just described, you just take this plane and you pass it through that transformation, then this boundary here gets mapped to this line here, and the one on the bottom gets mapped to this line. Yeah. Yeah, sorry, there's two R's. Yeah, so that's because I was talking about two different geometries. So in one case, I was talking about Minkowski space. So that was just ordinary Minkowski space. Now technically, it's a special case of Schwarzschild, but it's a special case with special properties. So it's usually not the best to think of it that way. So the one that's 0 here is this R in Schwarzschild, and the one that's in Minkowski space, and the one that's 0 here is the R in Schwarzschild. And so that's the fact that M is non-zero is what makes the difference. If M were 0, then indeed R equals 0 would be here. I mean, I should say in both cases it is the invariant definition of R is that it's the size of this two-sphere. Okay? But it's just the place where the size of the two-sphere is 0 is different once you turn on the mass. It's up here instead of here.
And as you said, it goes from time-like to space-like because of that switch.
That's right. Yeah. Yeah.
Well, so you started now this diagram with the capital X, capital T coordinate. If you would have just directly tried to do it with the original metric without having transformed the coordinate, would you have ended up in the same picture?
I would have just gotten this region. So that was what I tried to say over here. So the original R and T coordinates just fill this blue wedge here. And on the Penrose diagram, that's this diamond here. But then once you saw that, though, you'd say, well, this is silly because I can just fall through there. So there shouldn't be a boundary of the geometry there. I should extend it and see what's on the other side. Yeah, I mean, yeah. It's sort of it's ambiguous. In order to describe a geometry, it's not enough to just write down the one coordinate patch. You have to make sure that you've really covered the entire space with your coordinates. So this is a geometric picture. Any presentation of the Schwarzschild geometry would ultimately lead you to this picture, provided that you respect the spherical symmetry. And I should say, actually, you should think of this picture, right? So the space-time itself is actually 4-dimensional. So I've suppressed a two-sphere at each point. And then the size of that two-sphere is a function of where you are in this. So I guess sometimes people call that a warped product. So, you know, for example, these are lines where the two-sphere has size 1. This is where it's 0. Here's where it's infinity. Okay? Yeah.
You trim that part, but you could also identify it where you trim as a singular square. But I mean, I can deform this picture anyway, right?
Yeah. So, well, you can't. I mean, it's true that you can do transformations that kind of push this up like that, but they don't change the causal structure. So the simplest thing to do is to pick coordinates where it's a straight line. That's right. You can sort of, you can deform it in sort of ways that don't matter. That's right.
I don't get to see, I mean, why do you have like two different universes? I would say more like you have a redundancy, let's say, on your coordinates. Because if you get some x, whatever, x0 or x1, and then you have this minus x1, they both will give you the same r. It's your spatial coordinate.
No. But yeah, so R, you should think what R is really doing is it's just telling you how big the two-sphere is. But you know, nobody promised you that that's a sort of one-to-one map, right? I mean, it could be that the two-sphere has the same size in, you know, in two different places in the plane. I mean, and indeed that is what happens. So I don't think that you can say that this is an artifact because physically it actually means something, right? You can jump in from here and I can jump in from there and we can meet in the middle. But out here, I wouldn't have seen you, and out here, you wouldn't have seen me. So in that sense, it really is. This side is not just the same as this side. You could try and get rid of it by changing the geometry, but in order to do that, you'd have to put some kind of singularity here, and I don't want to do that. The rules I'm playing by is I'm looking for solutions with no matter, just solving Einstein equation. Okay, so it's good, actually, that's a good transition point now, because the fact that there's no matter is clearly a bad thing if we're actually trying to describe black holes. Because black holes are made out of matter. You know, you have some star sitting there, gets old, has a supernova, and the remnant collapses and forms a black hole. So where's all that in this picture? It's nowhere in this picture, okay? So the goal now is to describe real black holes. Of course, given that I went to all the trouble of introducing Penrose diagrams, that saves me now a lot of work because I can just introduce them at the level of Penrose diagrams rather than have to, you know, write down formulas for the matter and its equation of state and this kind of thing. So what does a real black hole look like? Well, the ones that actually form astrophysically are created by, you know, you have some cloud. So you start out, here maybe I'll draw it here so I can keep that Penrose diagram. So you start out in space-time that just looks like Minkowski space, okay? So this here is like the bottom of the Minkowski-Penrose diagram. And you've got some region in here where you've got a gas, okay? And then that gas is collapsing. And then at some point, it collapses to zero size and forms a singularity, okay? Oh, that was a skeptical. I'll give you a cleaner example in a minute. Okay. Now, outside of the gas, there's no matter present. And I'm going to assume that the gas is spherically symmetric, which means that outside, it has to look like the Schwarzschild geometry, or more accurately, a piece of the Schwarzschild geometry. But then once I get to the gas, there's no matter, and the solution can be different. So I claim that this is what the Penrose diagram actually looks like. In the past, you have just sort of ordinary Minkowski. So this past singularity has now disappeared. And then, you know, you evolve forward, the gas collapses, there's a horizon, and there's a singularity, but only one way. And so now, in particular, there's only one asymptotic boundary, which is good, I think. Well, so there's an I plus here, there's an I minus here, there's an I zero here. Now, I can even make this more concrete. So this still, you know, you might say, well, okay, you drew the picture, but what's really going on in this gas anyway. Why should you believe me? But there's actually even a simpler kind of black hole I can make. So rather than, this is like what happens in astrophysics. But we're theorists. So this is a very inelegant way of making a black hole. It's much nicer to just imagine, for example, that I just make a shell, spherically symmetric shell of photons, which are all collapsing inward. Okay? Don't ask me how I made it, but I made it. So inside that shell, you just have Minkowski space because no signal from the shell has gotten to you yet inside. The shell is way out 1 billion light years away. So you just have some piece of Minkowski space. So here's the shell. So remember, photons come in from J minus. Okay, so here's the photon shell. Now below the photon shell, I just have the geometry is exactly a piece of Minkowski space. And then, well, this is really not a 45-degree line. I should be fired. But okay, there we go. The shell collapses into 0 size and then forms a singularity. And now on top of the shell, well, still the geometry is spherically symmetric. There's no matter, so it's got to be Schwarzschild. So we can draw that like that. Okay? And now I've actually described to you what the geometry is. Down here, it's literally Minkowski space. Up here, it's literally Schwarzschild. What I've done is I've taken the Minkowski diagram. I've taken this piece of it. I've taken the Schwarzschild, I've taken the Schwarzschild diagram, and I've taken this piece of it, and I've just glued them together at the interface here. Being careful that the gluing obeys Einstein's equations, which it does, but don't worry about it. And that creates this geometry. So from now on, this will be what I'll call a real black hole. Not real in the sense of we see them in the sky, but real in the sense of we could make them in the lab, maybe, sometime. Yeah?
What comes first, the horizon or the singularity?
Well, it looks to me like the horizon, right? So so the horizon here is like that. So if you're coasting along here, you'll get to the horizon first. It's an interesting question whether you would notice that you got to the horizon. Here, it's manifestly clear that you won't, right? Because you're inside the shell. The shell is up here, and the geometry here is exactly Minkowski space. Exactly. No experiment that you could possibly do here could tell you that something funny is going on. But yet it is. This is one of the mysteries of horizons. Okay. Yeah.
So this probably just shows my lack of understanding of Penrose diagrams, but in both of these diagrams, when the black hole forms, you then have this wiggly line, which I guess is the horizon, which is extended.
Well, this is the singularity. So this is r equals 0.
Okay.
Yeah.
So
The horizon is here, and the singularity is here. Yeah.
Okay. So why does it look like a sort of non-local extended object in this
Well,
diagram?
yeah, it kind of does, but on the other hand, the sphere, so yeah, this is one of the downsides of suppressing the sphere here. So at r equals 0, the sphere has 0 size. So to some extent, it's not really an extended object. I mean, there's a sense in which it is, right? In the sense that if I'm here and you're there, we can't communicate, so we're somehow far away. But the space-time is rapidly collapsing around us. You can actually think of this as being sort of like a big crunch. It's like you're in a collapsing universe. And actually, the whole thing in this region, you can sort of think of it like you have a big bang, a universe that expands for a while, gets to a maximum size, and then contracts back to 0 and crunches. Okay, so that's actually basically all I was going to say about classical black holes. So I'm now going to take a foray into quantum field theory. So to make sure that everyone is happy with this, or at least reasonably happy. I should say I posted notes that are fairly complete, at least for the material of the first 2 lectures online, so you can look at them if you have more questions. You can, of course, also harass me. Okay.
I have one question.
Yeah.
There are some more advanced types of black holes which seem to be more realistic when they are rotating or something.
Yeah, yeah.
Does it have any bearing on
You know, so yeah, everything I say will be true for those black holes too. But, you know, it's just makes it harder to explain it, so I won't.
And the Penrose diagrams for those can be constructed.
Yeah, they can be. Yeah, they can be. Yeah, some of them look pretty crazy. But actually, for the ones that you create in nature, though, they always end up looking like this. Maybe one more piece of terminology, just because I'm sure I'll say it. These you can call one-sided black holes, and these are sometimes called two-sided black holes. Now, I've tried to instead call this the Schwarzschild geometry and this black holes, but I might accidentally use the other terminology sometimes. All right, so on to quantum field theory, now that we've learned general relativity. So unfortunately, this means that black holes are going to disappear for the rest of the lecture, but don't worry, they'll be back with a vengeance. Okay, so QFT. All right. So as Rob was explaining yesterday, a quantum field theory is just some particular quantum mechanical system. It's not something new. If you know quantum mechanics, you know quantum field theory. Well, okay. At least if you're a philosopher. But of course, it's a quantum mechanics that has certain special properties. So the main property of quantum field theory, which is important, is that you can write the Hilbert space as a gigantic tensor product over some small set of degrees of freedom at each point in space. Now, notice I said space, not space-time. So like Rob said yesterday, you know, when you're describing the Hilbert space of quantum mechanics, you work at a fixed time. And you describe the Hilbert space, and then later you evolve. So these degrees of freedom are like what yesterday, sort of the degrees of freedom were like the springs. So Rob was having this, like Rob would have this Hilbert space be the Hilbert space of a single particle quantum mechanics, you know, some spring. And then there would be one of those at each point in space. So a basis for this could be something like that. So this is if I consider, I'll consider the special case where there's only 1 degree of freedom at each point in space-time. So then 1 degree of freedom means that I can label states in the Hilbert space by giving you functions of space, okay, as a complete basis of the Hilbert space, which is just the set of all functions, which can be defined, you know. I guess if you like these kind of things, we can call it, okay. So that describes the Hilbert space. Great. Then to do evolution now that we've defined the Hilbert space, we need to define the Hamiltonian. So you know, usually you define in quantum field theory the Hamiltonian to be some integral over space. So for simplicity, to avoid Rob's confusion about d or d plus 1, I'll just always work in 3 plus 1 spatial dimensions. So this is a spatial integral. Okay. I mean, I shouldn't say that Rob is confused about it. Of course, Rob is not confused about it. Okay, so the idea is that the full Hamiltonian is some spatial integral of some local Hamiltonian density, where the Hamiltonian densities are essentially built just out of guys that act on these individual tensor factors. Okay. Now, of course, this can't quite really be true, or there wouldn't be any interaction between the two. So when I say local, I mean almost local. So this H can depend on, you know, the degrees of freedom at some point and on the sort of guys in the neighborhood, you know, but not more than the neighborhood. Okay, so that's a local quantum field theory. It's good to have examples. So you know, I'll talk about the same example that Rob talked about. What? The phi's? That's a good question. Okay, maybe I'll make that ideological comment now. Okay, so yeah, there's a nasty business here, which in terms of this, you know, the Hilbert space is sort of doubly infinite dimensional. It's infinite dimensional just at each point. If you have a particle there, you've got an well, Rob was calling them x's, but I'll call them phi's to avoid getting confused with these x's. You have a phi at each point, which has its own momentum conjugate, where phi commutator with pi is I. So that's an infinite dimensional Hilbert space. And then you've got an infinite tensor product of those infinite dimensional Hilbert spaces. And therein lie divergences. Okay. So in particular, if you really consider arbitrary discontinuous functions, then as soon as I write down any kind of Hamiltonian, then almost all of the states will have infinite energy, and we won't care about them. So that's sort of the dirty secret of quantum field theory. Now, there's two ways of dealing with this. One is to do what Rob did, which is to just include the lattice from the beginning. And logically, this is the correct thing to do. But as a practicing quantum field theorist, what you usually do is you have the lattice in the back of your mind, but you write the continuum equations, okay? And then whenever you run into trouble, then since you've sort of been remembering the lattice all along, you just bring it back at that point and solve whatever confusion it is that you encountered. And I'm going to adopt the second school, even though it's a little more confusing, just because otherwise the notation becomes impossible. Okay, so the kind of Hamiltonian that we like to write down, say for a scalar field, is like that. So that's one of the simplest theories is a free scalar field. Okay, so this pi, so the phi, we know what phi is. We know how it acts on this basis. The pi is just, as usual, defined as the derivative with respect to phi acting on the wave function in a Schrodinger representation. So now I've defined both of these as abstract operators. I've defined the Hamiltonian as an abstract operator. So I've defined the quantum mechanical system. We can compute whatever we want. Well, in principle. Now, I should say that, well, yeah, I guess, yeah, maybe it's worth saying that writing out the commutators. So just in case this isn't familiar. So you can look at the commutation relations of phis and pi's at different points in space. And it's given by some delta function. And then you can also have that phi of x, phi of y commute in general, and the same with the pi's. So the only comment to make is that these commutation relations are consistent with this tensor product decomposition. So remember, I defined the different phi's at different points to be acting on different subfactors of the Hilbert space, and the same with the pi's. So they better commute, and indeed they do. All right, so that's the sort of basic operator structure. Now, in conventional quantum mechanics, we're usually interested in, finding the ground state. Okay, I guess by conventional, probably here I don't mean, I don't know, quantum communication or something. I'm thinking more along the lines of condensed matter physics, atomic physics, this kind of thing. You have a Hamiltonian, you want to find the ground state. That's what physicists do, right? So Rob yesterday described for you the ground state of this Hamiltonian, so I won't write it again. It's some formula. It's e to something which is quadratic in phi. And actually, on the homework, I have you compute that ground state in two different ways. Just because, this is one of the few cases where you can actually compute a ground state in quantum field theory, and it's fun to do it. And if you can do it, then it will be clear that you sort of understand the basic formalism. Which, of course, is the real goal of any homework. But, rather than trying to write down the vacuum wave functional explicitly, since that's usually too hard, what we usually do in quantum field theory instead is we study the expectation values in the vacuum of Heisenberg picture operators. Okay, so what are those? Well, we just define phi of t in x. So I'm sure this everyone knows, but I'll just write it anyway. Okay, and then we're interested in computing things like, so say omega is the vacuum state. Then we're interested in things like okay, that's the kind of thing we like to compute. It's the correlation function of two phi's. Okay. Now, in order to compute this kind of thing, and so I could just tell you what the answer is, and in a minute I'm going to, but I want to go a little bit of the way towards computing this, just because I'm going to need to introduce some technology that when we get back to black holes is going to be important. Okay. So what do we do here? Well, the thing that you do is you observe that this is some Hamiltonian system, and it means that this phi as an operator obeys some dynamical operator equation, just the classical equation of motion of phi, updated to an operator equation. And the equation is, in relativistic notation, d mu minus m squared acting on phi is 0. Okay, that's it, which is the wave equation. Okay, so anyone with undergraduate physics knows the wave equation. So the goal then is that we want to write down an operator solution of this equation. So the obvious thing to do is to pick some sort of basis of solutions of this equation. It's a linear equation, so that you can superpose solutions and get another solution. So you want to write down phi as some sum over some basis of solutions Fn. And then there's going to be an operator coefficient of each one of those solutions. And this n is just labeling the solutions. So clearly, any operator solution of the equations of motion, I can always expand this way. Maybe it's not completely obvious to you if you haven't seen Fourier transforms before. I'm gonna write it out now explicitly by picking a particular set of the f's. Oh, oops. Okay, so obviously everybody's favorite solution of the wave equation is plane waves. Okay, so here's the solution. Where omega k is just the usual relativistic formula for the energy, then so phi, and okay, for ideological reasons, it's actually convenient to normalize this like that. Okay, so this is some choice of Fn, some choice of solutions. These solutions are labeled by a 3-vector k. Once I know k, I determine omega k from this formula. Okay, so it's a 3-dimensional space of solutions. Then, well, okay, so apparently, so then, oh, I went to the trouble of including the normalization. Plus e to the minus I k dot x plus I omega kt, ak dagger. Okay. So great, I guess. So I mean, clearly I can do this because these ak and ak dagger are just the operator Fourier transforms of the operator phi. Okay. So I can always do the inverse transform. So far that's all I've done. Oh, sorry. Yeah, let's just keep it lowercase. Yeah. Good. So okay. So great. We solved the operator equations of motion. So what? Well, the good news is that I guess they're covered up now. But we'd worked out the algebra of phi and pi. Okay. And since we know the algebra of phi and pi, that imposes an algebra on A and A dagger. Okay. And this is the algebra of the creation and annihilation operators that somebody was talking about yesterday. I guess Frank certainly was talking about it yesterday. I don't remember if Rob was talking about it. And the algebra is, I write it here, that AK prime dagger is some delta function and that A commutes with all the A's commute with all the all of the A's commute with each other. All of the A daggers commute with all of each other. And then finally, and this is an important one, the Hamiltonian commutes doesn't commute. It has this relationship with A. Okay. So of course this is just the simple harmonic oscillator. So anyone who's thought about the simple harmonic oscillator is fine with this. So I don't want to belabor it. The point then is just that the vacuum state, the ground state of this theory, because of this, is just the state which is annihilated by all of the A's. Okay? And then on top of the ground state, you build excitations by acting with A daggers. And you can, with each A dagger you act with, you can pick the K. And this is how you create particles. So, moral of the story, you find solutions of the wave equation. These solutions are going to be called modes. Okay? For any set of modes, you can introduce a set of creation and annihilation operators which create particles in those modes. And that describes a complete basis of the Hilbert space. The relationship between this basis and the basis I started with, the phi basis, has to be worked out. And for the ground state, you can work it out and get the formula that Rob wrote down. And then you can get the excited states by re-expressing the creation operators in terms of phi and pi and acting on the vacuum. Okay, and both of these bases are important and interesting in quantum field theory, and you don't understand it until you are comfortable in both, which is why I wanted to introduce them. All right, so finally, let me get back to the two-point function here that I was talking about. Okay, so I'm not going to compute it for you just because you can roughly see how you would do it. You take this expression for phi, you plug it in here, and then you use the algebra of these A's and A daggers to move all of the A's to be acting on the vacuum. And then in the process of doing that, there'll be something left, and that something left will be this correlation function. You're welcome to do it on your own if you like. Yes?
I missed this. Why did the range of phi now become an operator? So you had first said phi goes from R3 to R, and at some point...
No. The Hilbert space was spanned. There's a basis of the Hilbert space where each basis element is labeled by a function from R3 to R. Yeah. So then the operator phi acts. So if I act, that was why I put in the capital, but then I was worried it might be confusing. If I act with the operator phi of x on the basis state phi, so let's call this a particular. So phi hat here means that I have a particular function in mind. Phi hat is this phi is an operator. Okay, I act on a particular basis element which is labeled by a particular function phi hat, and what I get is phi hat of x acting on the state phi hat.
Okay, and this x that you give to phi, is it the position operator?
Yeah, it's the position. It's not an operator. Position is not an operator.
And which of the phi's currently on the board are which?
It's all currently all phi's on the board are operators except for this one, which is labeling a state. Okay, and this one is an eigenstate of the operator phi, so it's consistent. Yeah, phi is always an operator. Okay, so right, this two-point function. So it's some function. I'll write it down, but we don't really care about the details of the function. We just care about its properties, which I'll describe to you. Okay, so this is some Bessel function, but the details of the Bessel function don't matter. You only care about two things about this. So I should say, it's important here. So when I do this, I'll choose the points to be at a space-like separation. So maybe I'll just comment. When I want to diagnose properties of the vacuum state, it's best to compute things at space-like separation. If I compute things at time-like separation, then you're now sending signals, and that's a different kind of question. So for now I'm going to focus on space-like separation. So then you get this. Okay, comment number one, this is not zero. Okay? Now that's interesting. In non-relativistic quantum mechanics, if you work in the ground state, it's boring. Think about a bunch of massive particles floating around in some gas. What's the ground state? They're all sitting on the floor. Okay? There isn't any interesting correlation. Here there's interesting correlation. Okay? So something is really happening in the vacuum. And what's happening is entanglement. And I'm going to try and make that more clear in a minute. In a minute or two. But for now, let's just emphasize this is not zero. Okay? Now, what does it do? Well, okay, so the asymptotic behavior is interesting. So it scales like e to the minus m x minus y for x minus y much greater than m inverse. And then it scales like 1 over x minus y squared for x minus y much less than m inverse. Yeah.
Did you just say what this K1?
It's some Bessel function. Yeah. M is the mass that appeared in the Hamiltonian, which I erased. Yeah, M is a parameter in the Hamiltonian. Yeah. So, so these generic properties are true in essentially, this type of behavior is essentially true in any quantum field theory. So of course I was studying free quantum field theory here, and I got some answer. But this general kind of behavior is something that you should basically expect to happen in almost any quantum field theory. Now, at large separation, the correlation function falls. There will be some scale m, or m inverse is a length scale. Condensed matter physicists like to call m inverse the correlation length. For separation large compared to the correlation length, the correlation function dies exponentially. And then when you bring the 2 points together, much closer than the correlation length, then you expect power law divergences. Okay? So it gets more and more correlated. And this is what Rob was saying yesterday, right? He was talking about how he has his entangling surface, and as you bring the 2 points towards the entangling surface, they get more and more correlated. That's what this correlation function is saying. Yeah?
Could you relate that number, the power 2 with the dimension?
You mean dimension of space-time? Yeah, definitely, but I'm working in 3 plus 1. Yeah.
It's always Gaussian.
This is d minus 2 if you're working in d space-time dimensions. Yeah. That's for a free scalar field. Now, it's worth saying that a case that you're often interested in is m goes to 0. Okay? If m goes to 0, the correlation length is infinite. And then you've got power law behavior all the way out. And the theory is scale invariant. Because once m goes to 0, there's no dimensionful parameters left in the problem. And you get what Rob called a conformal field theory. That's eventually going to be important for me. It's probably going to be important for Rob before it's important for me. But that's a conformal field theory, a field theory with no scale where you just get scaling law, power correlators all the way out. Yeah? Well, yeah, so far I've been doing everything in Minkowski space. So if you like, here's the Penrose diagram, and I'm picking one of the points to be at the origin of polar coordinates here, and then I've got the other point here, and I'm just studying how it behaves, either as I pull it that way, or I pull it together with the other point. But it's space-like separation, whereas a time-like separation would have been putting the point up here, and that's what I'm not doing. Yeah. Oh, you mean because I use the word conformal in both cases? Yeah, so actually, yeah, the conformal field theory, actually, if I'd done this conformal rescaling of the metric, I would have gotten the same theory before and after. Okay? But that's only true in a conformal field theory. Actually, I think Rob has you checking this in the homework. Okay, so let's see. Will you let me have 5 more minutes, or should I?
We should probably cut it short because it's only a 15-minute break.
Oh, okay, great.
If you want to just wrap up.
Okay, so let me just wrap up then. So okay, so today we got through classical black holes, and we got through some basic properties of quantum field theory, some of which Rob also said, but I figured they were sufficiently important that it's worth saying again. So I mentioned briefly that we should think of this correlation as coming from entanglement. So to this audience, that should be obvious. Okay, the system is in a pure state, so there's no classical correlation of any kind, but yet I found correlation. Okay, that's entanglement. In the next lecture, I'm going to try to be more explicit about the structure of this entanglement. Rob is also going to do that, but he's going to do it in a different way than I am. He uses entanglement entropy. I'm going to use what's called the Rindler decomposition, which is more useful for then later generalizing to black holes. And then from there, once we're happy with quantum field theory in Minkowski space, we'll move on to quantum field theory in the black hole background and see how it goes from there. All right, thanks.